All right, in this section, we're going to discuss the Lorentz transformation. Suppose a spaceship moving with a speed of 0.5 c, as observed by a stationary person on Earth, launches a missile with a speed of 0.75 c, as observed by a person on the ship here. What speed would the person on Earth observe the missile to be going? We already explained at the beginning of this unit that we can't just add the velocities as we normally would in classical mechanics. If we did, we would get greater than 1. 0.5 times 0.7. 0.5 plus 0.75 is 1.25 c, which is not possible. This is faster than the speed of light. Okay, so what we're going to do in this section is talk about how we can solve these kinds of problems. The Lorentz transformation relates the velocities in two inertial reference frames. So I have an equation here. It looks kind of similar a little bit to what we've seen before, but let's talk again about these variables. U is the relative velocity of the two frames. Again, observers in both frames agree on the velocity, but will simply express it in opposite directions. So Vm is the velocity in the frame that's considered to be moving. Vs is the velocity in the frame considered to be stationary. These are velocities for the same object, just observed from two different reference frames. So we're going to take this idea back to our rocket ship and our missile and our stationary observer on the Earth. Okay, so just as a reminder, the ship is moving 0.5 c with respect to the stationary observer and launches this missile 0.75 c with respect to the ship. And the question we're asking is, how fast is this missile moving relative to the stationary observer? We're looking for the velocity of the missile as observed by an observer in a stationary reference frame. U is equal to 0.50 c. The observer sees the ship moving at this speed, and the ship sees the Earth moving past it at the same speed. This is the agreed upon speed. We know because this is with respect to the observer, so the observer sees this 0.5 c, this velocity of the ship. Vm is 0.75 c. The velocity of, and m doesn't stand for missile, okay, which can be a little confusing. It's the velocity of the moving reference frame. So the velocity of the missile in the moving reference frame. Why? Because the ship launched the missile at 0.75 c relative to itself, but the ship is still moving and the missile is moving. So what is Vs, the missile's velocity in the stationary frame? So now that we've sort of unpacked what we know about the situation, let's use our equation for the Lorentz transformation to find the velocity of the missile relative to the stationary observer. All right, so here's our equation, our Lorentz transformation equation. It's already solved for what we're looking for, so we just have to substitute our variables. And we can keep them in terms of c. Some will cancel, they won't all, but so Vm is 0.75 c, U is 0.5 c, divided by 1 plus U times Vm, so 0.5 c times 0.75 c, divided by c squared. The c squareds on the bottom, this fraction on the bottom, cancel. And we have 1.25 c divided by 1 plus 0.375 is 1.375, which is 0.91 c. So the observed velocity from the ground is greater than the missile's velocity in the moving frame of reference. So in the moving frame of reference, it was only 0.75 c. So it's greater than that, but it is less than the speed of light. So if we had just used our classical mechanics to just add the two vectors together, we got something that was greater than the speed of light, right? We had gotten 1.25 c. So we're still getting something less than the speed of light, but it is greater than the velocity in that moving frame of reference, that 0.75 c. All right, here's an example problem of a Lorentz transformation. A spaceship approaching an asteroid at a speed of 0.600 c launches a rocket forward with a speed of 0.400 c relative to the spaceship. Okay, so here's the spaceship. It's moving. It's approaching the asteroid at 0.006 c. This is relative to the asteroid. Okay. It launches a rocket forward with a speed of 0.400 c relative to the ship. What speed is the rocket approaching the asteroid as measured by an astronaut? So over here is the astronaut on the asteroid. Okay, so that's my stationary observer, right? So this is a lot like the previous example problem. So in this case, the agreed upon velocity here will be the velocity of the spaceship, 0.600 c, because it's relative to the at-rest observer. The spaceship is approaching the asteroid at 0.600 c, but from the perspective of the ship, the asteroid is also approaching at that same speed. Okay, now the velocity of our moving reference frame is this speed of the rocket because it's relative to the moving reference frame, the ship. The ship is moving, right? So we need the velocity from the perspective of this stationary reference frame of the asteroid. So that velocity of that stationary reference frame, or from that perspective, is Vm plus u over 1 plus u Vm over c squared. Okay, so from here, all you need to do is substitute values. I'm going to stop here on this slide now, and on the next slide, I'll show all the work of substituting these values and getting to our answer. All right, so in the previous slide, we left off by identifying our givens, and I'd written this equation, but now we just need to substitute our values. So substitute for Vm 0.4 c and for u 0.6 c. Then on the bottom, I just multiply them. And again, the c squareds cancel on the bottom here. So we have 1c divided by 1.24, which is 0.806 c. So here's the cool thing. That's faster than the speed that it's launched out of the spaceship with, right? That was 0.400 c relative to the spaceship. So it is faster than that, but again, still less than the speed of light.